Hello, students. We're going to talk today about measurements and their abbreviations. And so let's go ahead and get started. We are going to be looking at the metric system and the International System of Units in Science. And so here's the main units of measurements and their abbreviations. For length, we have the meter. And that is the same unit both in the international system, which is the SI system, and also the metric system. In volume, the metric system is the liter, which you're familiar with like beverages like sodas and stuff. The SI unit is the cubic meter. And next week, we're going to be looking a lot at how to interconvert between different kinds of units. In mass, the SI unit is the kilogram. Metric system is the gram. And just to make sure you realize that the SI system is the international system of units that's used in science. Now, in the case of the mass discussion, normally if we were in a chemistry lab, which unfortunately you're not in there this round, we weigh out a lot in grams. So it's going to feel like that's the official unit for us in science because that's what the quantities we usually measure out in chemistry. But officially, it's the kilogram. Temperature, degrees Celsius is the metric system. The SI unit is the Kelvin. And we will be talking about kelvins when we do the gas laws chapter, but that's a little bit further down the road. And then time is in seconds for both. Okay, so let's talk about length. In the metric system, NSI, it's meters. Chemistry uses a lot of centimeters. And so in a few moments, we're going to talk about how we read from a measuring device. If you notice here is the inches that you might see on a ruler. Inches is an English unit, so we don't use that. If we were to measure the length of something in chemistry, we would use a meter or a centimeter. And here's a relationship of 1 inch. If you notice here, 1 inch going across is 2.54 centimeters. Now, do you have to memorize that? I'm going to be giving you a list of relationships that we're going to use to convert, and I'm going to be putting those on Canvas. But this one here, the 1 inch equals 2.54 centimeters, that is something that I would give to you. Okay? All right, so here, if you notice, I'm going to write on this. I don't like the red smooth, purple. 1 meter is 100 centimeters. This one I would like you to know and memorize because we're going to need it a lot. The rest of these would be given. Now, do I think it's a good idea that you know that there's 2.54 centimeters in an inch? Maybe, but I just want you to focus on what is super essential, which are the metric to metric relationships. Now, 1 meter is 100 centimeters. So the prefix centi is 100. But sometimes I'll tell you what's a little bit confusing about metric system is that 1 meter is 100 centimeters, or you could write it as 10 to the 2 centimeters. But there's also another way of looking at this. 1 centimeter is 10 to the negative 2 meters. So 1 centimeter is a fraction of the large meter. Which way do I recommend? I recommend learning that 100 centimeters are in a meter. Okay. Why can this be confusing though, is if you look up the word centi in your book, it's going to show it with the 10 to the negative 2 as its relationship. So I think that throws students off. So what I want you to do though is just memorize this one and understand that 1 meter has a whole bunch of centimeters in it, 100 of them. Okay. Volume is measured in cubic meters in the SI system. And in chemistry, though, the one that we prefer and that we use the most is liters or milliliters. So another important relationship that you should know is that there's 1,000 milliliters in 1 liter. Now, where does this whole cubic business come from? Let's say that you have a room that has a certain volume to it. So I guess my room here is looking like a giant cube. But if you were to determine what the volume is of this room or this cube essentially in this pic, what you could do is measure the length of the cube times the height, right? Times the depth of it. Actually, that was the depth there. So what you do is you'd have these 3 measurements, right? And then to get its volume, you'd multiply. The volume would equal the length times the width times the height. And so since you're going to multiply those 3 numbers together, then the unit's going to end up being multiplied. So let's imagine that I measured the length of this cube, or I'll just say room, in meters. Then meters times meters times meters would give us a cubic meter. Okay, and now a little bit later in the class next week, we're going to talk about how we can interconvert between these two, because this does not seem like it has anything to do with the liter, but it does. And I'll tell you why, is that there's this thing where if I have a cube and we determine its volume in centimeters, then that volume is cubic centimeters. Well, it turns out that 1 cubic centimeter is 1 milliliter. And that's going to be our relationship that kind of ties together these cube units and the metric system liters. Okay? So out of these relationships, which one's the important one to know? 1 liter's 1,000 milliliters, and I would know that. Everything else would be given. These would be given, and this one would be given. But I will say that it wouldn't be such a bad idea to understand that 1 milliliter is 1 cubic centimeter. Okay, but I still will give you that relationship. Okay, when you weigh an object in our lives, we weigh ourselves, let's say, on a balance in pounds. But in chemistry, we usually weigh things in grams. So this picture is showing a picture of a coin, and it's 5.01 grams. Okay, and so grams is very common in a chemistry scenario. The one that I would know regarding relationships, 1 kilograms, 1,000 grams. This one I would know. And then for your, I really think it's important that you should know that 1 kilogram is 2.205 pounds. Now, I'm still going to give that to you because I want you to know your metric to metric really well. But for nurses, this one's going to be important because you're going to weigh people in pounds, but when it comes to like dosages of medications, they're usually not in that English unit. And we are going to practice conversions of that next week. Okay, temperature. Temperature is measured in Celsius. So in our labs, we have thermometers that measure in Celsius. There's also what's called the Kelvin scale. We're going to come back to this when we do our gas laws chapter. And in this case, this thermometer was reading 18 degrees Celsius, and that could be converted into another very common temperature scale called Fahrenheit. When we are discussing allied health majors, temperature is important because nurses take temperature readings for patients when they come in. So in that case, normally temperatures are recorded as 98 degrees Fahrenheit as a kind of there's a range within there that's considered normal. But a lot of times too, I think it's important to be able to interconvert between Fahrenheit and Celsius. And later we'll have some equations that will help us to do that. Time is based on seconds. So doesn't mean that that's the only unit of time that there is. A lot of chemical changes, we talk about like how fast they happen. And so seconds is very common, but it could also be hours, days, minutes. A good example of where time would come in would be like the radioactive decay of, let's say, a sample of uranium. Like that, when we talk about how long a uranium sample might take to decay in radioactive chemistry, that could be 100 million years. So it's not, seconds isn't the appropriate unit. But in allied health majors, when they use radiation in terms of, let's say, testing for tumors in the thyroid, they might inject you with a radioactive element. And when we talk about how long it might take for those to decay, we're usually looking at hours, sometimes days. So anyways, I just wanted, we're going to do a chapter on radiation, but I just wanted you to get the feel that seconds is the most common unit, but it's not the only unit of time that you'll encounter in chemistry. Okay, so you can take a minute to go through this. You can pause me and you can determine which one of the following is shown. You know, is it length, mass, or volume? So a bag of onions has a mass of 2.6 kilograms. That is mass, right? A person is 2.0 meters tall. That would be length. A medication contains 0.50 grams of aspirin. That's mass. And a bottle contains 1.5 liters of water. That would be volume. Okay, just like I did in class, I think you guys can take a look at these, practice these, and then you have the answer on the next slide. So you can pause, do these, and then, oh, actually that one didn't have it, so I'm sorry. So this is just looking at common ways of, for the SI units. Okay, so for the SI units, John's height, the official unit for height in SI units would be the meter. So that would be number 3, 2.1 meters. The mass of a lemon in the official SI unit would actually be kilogram. And the official SI unit for temp would actually be number 2, which is Kelvin. Okay. Okay, so in class we practice writing scientific notation. This was used to write out very large or very small numbers. So the width of human hair is very small, 0.000008. If you notice, that's really hard to describe. So instead, what we do is we convert it to scientific notation. So our thing to consider is you're going to pick a number between 1.0 and 9.9, because that's be less than 10. Okay, that's our range. And then what you're going to do is you're going to pick that number. So in this case, we pick the number 8. So there's our 8. And then we're going to count how many places we go to the end of the number. So 1, 2, 3, 4, 5, 6. So then that's our exponent. Now, the fact that this is a very small number means that the exponent is negative. Okay, the number of hairs on a human scalp is 100,000. Now, how would I write that? My number is 1. 1, and then here I am, and I'm going to go 1, 2, 3, 4, 5 times 10 to the 5. I know that that is positive because it's a large number. So large numbers have positive exponents. Small numbers have negative, exponents. Okay. Okay, so the scientific notation value would be the coefficient, the number has to be between at least 1 but less than 10. So in this case, our coefficient's 1.5, and then the power of 10 is 10 to the 2. So if I'm looking at this as scientific notation, what that means now is that I'm multiplying 1.5 times 10 times 10. That's what that means. And that would end up being 1.5 times 10 times 10. That's 150. So that's the number that 1.5 times 10 to the 2 means, 150. Okay, so 5.2 times 10 to the 4, that's the same thing. Now this starts to get trickier and cumbersome to write out. Is you're multiplying 5.2 times 10 4 times. Now, what's the easiest thing to understand about it is what you really are doing is you're moving the decimal place at the decimal point 4 spaces to the left. So if you're at 5.2, you would say, okay, that's 1 decimal place over 2, 3, 4. So that is 52,000. Okay, if I have 3.78 times 10 to the negative 3, that is the same as dividing by 10 3 times. And what's that going to do is you're going to start here. So here's our number, and that would be this way 3 times. So 3.78 times 10 to the negative 3 is the same as 0.00378. Okay, so when we have scientific notation with positive values, those are bigger numbers. And then scientific notation with negative numbers means smaller than 1. Okay, small numbers. And why is scientific notation so important in chemistry and in science is that in science we typically have very big values or very small for the most part. So Look at the bottom one there, the mass of a bacteria. Look at how tiny the measurement is for that mass. So that would be a nightmare to write out. So instead of writing that number with all those zeros, we'd write 1 times 10 to the negative 19 kilograms. Okay, the time it would take for light to travel from the sun to the earth is 500 seconds. So that one's not so bad. So, I'm looking at these numbers here, these two values for the mass of a typical human in kilograms. Those aren't so bad. Do I need scientific notation? Maybe not. But certainly for these other numbers that are so giant or so tiny, scientific notation's really helpful. Okay, so let's practice one more thing here. We'll keep practicing a little bit. I'm going to pick my decimal between 1.0 and 9.9. Then I'm going to do 1.28, and then I'm going to say 1, 2, 3, 4, 5, 6, 7. So that's where the times 10 to the 7 comes from. Coming down here with the diameter of a virus, I'm going to pick the number 3, and it's going to start there, and that's 1, 2, 3, 4, 5, 6, 7. So, and then notice that's a small number, so that's why that's times 10 to the negative 7. Okay, so for the class, I would like you to bring your scientific calculator to class next Tuesday, and I'm going to go through how to plug in numbers in using scientific calculators. This doesn't mean expensive. You can get an inexpensive calculator, but what this does mean is you do need one with an log function, because that'll tell you that it has the keys that we're going to need. And one of the keys that we do need is the ones that say EE or EXP. So we'll talk more about that on Tuesday. So I wanted students to be able to bring it to class. Okay, so take a moment to write the following number in scientific notation to practice. You can pause me and then work on that. Okay, so our decimal is 5.8. And then it'll be 1, 2, 3, 4, 5. Did I count that right? I got shaky. 1, 2, 3, 4, 5. So that should be times 10 to the negative 5. And we want to get used to writing the units, so that has grams. So I'm going to write it in grams. Okay. Take a moment to select the correct scientific notation for this number. So my value that I'm going to select is 8, and then I'm going to say, I'm going to be here, right? 1, 2, 3, 4, 5, 6. So this would be times 10 to the negative 6, because the number is small. And let's hope that I moved it right. I'm going to count it again. 1, 2, 3, 4, 5, 6. Yes. 7.2 will be my decimal here. And then I'm going to count 1, 2, 3, 4 times 10 to the positive 4. Okay, going from scientific notation to a standard number this is 2.0 times 10 to the negative 2. So it's small, right? So that has to be tiny. So I need to move this decimal this way. 1, 2. So that would be 0.020. So that would be this value. And then 1.8 times 10 to the 5 would mean that I move the decimal point 5 places. And that would get me to, so here, that's 1 by moving it there, and then 2, 3, 4, 5. So this would be 180,000. You can check yourself here by 1, 2, 3, 4, 5. Okay, so we had that. Okay, so one of the things that we started to talk about was looking at measurements. And this is actually really important for scientists because we want to be able to measure things correctly and convey to somebody what kind of measuring devices were used. So in this case, we have a centimeter ruler, and it's marked in 1 centimeter at a time. So 0, 1, 2, 3, 4, 5. Everyone looking at this number would know, and nobody would argue, that we're at least 4, right? This is the marking. Now, between 4 and 5, we envision in our mind that there's 10 markings that are going to slice that up. And so I look at that and I would say, oh, I think that that is 4.5. And I'm going to write the unit. Okay, somebody else in the class, I believe, said 4.6. Somebody else might have said 4.4. Okay, notice what happens is that everybody's in agreement on the 4, but the tenths place is what's called the uncertainty. Meaning that it's our guess or estimate. And the guess or the estimate is important here because it is, there's always going to be uncertainty in a measurement then, because what will happen is you have the markings, but then you're allowed one more guess, 1 digit beyond that. Okay. And what this means is that we would expect among a series of people using this ruler to record measurements that there'd be this natural fluctuation somewhere in between 4.4 and 4.6. So one thing I didn't mention in class is that if I decide that 4.5 was what I thought it was, then I'm assuming that this is plus or minus 0.1 centimeters. Now we can't take any random guess. We can't say this is 4.8 centimeters. That's too far off of this. And we can't say 4.5129. That's too much. So you just allowed 1 digit over from where it's marked. Okay, that's just exactly what I said, but in written part, you can slow this down and read it. Okay, so this is again, here's our range that we would expect, somewhere between 4.5, 4.6, 4.4, somewhere in that range. Okay, now if I have a centimeter ruler where it's better marked, then I look at this now and I know based on those markings that it's 4.5. So let's look, 4.1, 0.2, 0.3, 0.4, 0.5. So for sure it's that, but it's somewhere between 0.5 and 0.6. So now I can take the reading, make a guess. I look at that and I'm going to say 4.56. Like that's what I think it looks like. But there's going to be some variation among you and me and everybody in the class. And so this is now our uncertain digit. That's our uncertainty. And notice what happened. Our uncertainty is in the hundredths place. It's further out. Now, why is this important is that in science, we want more precision. We want more decimal places because we're more likely to be closer together in our measurements. And so what we'll see with this ruler is we see an increase in what precision is of our device, which means that our measurements are closer together. To one another every time we take a reading on here. Okay, so precision is based on the markings of the measuring device. So precision is based on markings of the measuring device. Okay, so if you want more precision, you better have better markings on whatever device you're using. And by better, I mean it needs to have more sliced up into smaller intervals or increments. So if I was to pick which of these two I would use this one because it's marked in the tenths. So it's marked in the tenths place. So our guess or uncertainty is in the hundredths. And that's better than the previous ruler that we read. Okay. Oh, I want to go back to that. Okay, so in this case, this is a good slide because it shows us where students will struggle with this. So if I have this centimeter ruler and it shows at 3, it's marked in 1, 2, 3, 4, 5. Then if it's exactly on the 3, you have to be careful because most students will just write 3 centimeters. But remember, if it's marked in the ones, we can take our guess 1 digit over. So the correct reading is 3.0 centimeters. And don't forget that that is important to take that guess, even if our guess is 0. We cannot say 3.00 centimeters, though, correct? Because it's not that well marked. It's only marked in the ones. So the guess is in the tenths. Okay, try this one. This one has I know it looks a little weird. This is showing 9 to 10. So this is 9 centimeters here. Just the graphic's a little funky looking, 10 centimeters. And then it's marked in 9.1, 0.2, 0.3, 0.4, etc. So go ahead and take a moment to figure out what might be appropriate reading for that. You can pause me and think about it. I'm just going to fix that funky looking 9 that I wrote. Okay, so if it's marked in tenths, then you are allowed. Okay, well, really what this means is that this is 9.0. So for sure we're at 9.0. That's marked. But now we're allowed our guess. So if I'm looking at that, if I'm reading that, would have probably put 9.02 centimeters. But the important part is that that's in the hundredths place is the correct reading. So either numbers 2 and 3 are appropriate. Okay. The estimated digit then might be slightly different, but both readings are okay for this. Okay, so when it comes to this discussion, let's think about what we just talked about is we're taking readings from measuring devices. And those numbers that we get from the measuring device are significant figures. So this is, number one, is for, don't ever forget this, this is for measured values, not for exact numbers. Not if you're like, oh, I have 2 apples in front of me. That's not a measurement. Things that you're reading, thermometers, things that you're reading, thermometers, rulers, those are things that are measured values. That's where significant figures would apply. So in the last examples, we talked about how we read the measuring devices. All those numbers we read off the device were significant figures. So let's just kind of see how we can determine how many sig figs something has. I skipped this slide in lecture because I want to get to here. Let's say these were measurements recorded that were actual measurements. These are easy because if the measurement is shown and they're all non-zero digits, it's just how many digits they have. This has 4, this has 2, this has 3, this has 5. So if they're measurements, and we know that from these units, centimeter for length, feet for length, pounds for mass, okay, you're getting the point there. But any number shown that's a non-zero digit's easy, it's significant. Okay, 50.8 millimeters, 3 sig figs, 2001, 4 sig figs. The one I want to focus on the most is this one here, the 0.0702. That is only 3 sig figs. I know there's these 2 zeros out in front, but the 702 is measured. Okay, the other 2 zeros out in front are just telling us, they're what are called placeholders. They're telling us where the decimal point is. Now I want you to notice, if I convert this number to scientific notation, those zeros disappear because where do they go? They go into the exponent. So the 7.02 part is the only part that was measured. Okay, so this is going to be something that'll come up later as we start to do some calculations, but those initial zeros that are absorbed into the exponent there, those are not significant. Another way of telling you this, as far as an official rule, is that you have a number, but if there's not, if the zero is shown and there's not another digit out in front of it, it's not significant. Okay, so let me put that into perspective. If I have 50.8 millimeters, okay, this zero has a non-zero digit in front. So that makes it significant. Now, if I convert this to a meter, that's going to be 0.0508 meters. So we're going to look at how we can easily do that next class, how we're going to flip back and forth. But for now, let me just tell you this, that if I record using a ruler 50.8 and then somebody says, oh, I need that in meters, I would divide by 1,000. Now notice the zero came up. That's because it is smaller. That is not part of the measurement. Another way of proving that to you is I can convert this to scientific notation. And notice what happens. That zero goes away because it's not part of the measurement. It's just telling us where the decimal point is. Okay. The last one here, 0.40505, that has by sig figs, those zeros in between non-zero digits are not confusing to students, so that's fine. Okay, 50.80. Now this zero has a non-zero digit before it and a decimal place too, so that one's fine. Okay, right, you have a decimal place. Okay, but I prefer, instead of you thinking of it by some rule, that you understand what we were looking at earlier is that is the guess. That zero on the N is the guess, the uncertain digit. That will make it significant. So significant figures are the numbers from the markings plus your one guess. In other words, they didn't just put it on there for the heck of it. So something like 40.00 grams. These numbers here are all part of the measurement. That last zero that I'm highlighting with the arrow, that's our uncertainty. And so that has 4, as does this top one. Now, you see this 200 here? Okay, showing the 200 with that dot is trying to tell you that all 3 of those are significant. But a better way of writing this is to put it into scientific notation. If I really want to show those zeros as significant, I should probably write this as 2.00 times 10 to the 2 minutes. Any digits shown in scientific notation will be significant. So that is 3. Okay, 0.440. Again, I look at that zero. That's our guess. There's a non-zero digit and a decimal point before it. So that's 3. 0.022 is only 2 because these guys don't have a non-zero digit in front of them. And if we go and we convert this to scientific notation, that would be 2.2 times 10 to the negative 2. And if you notice, that 0 goes away. I can convert this one to scientific notation, and that's 4.40 times 10 to the negative 1. Notice that 0 stays because it's part of the measurement. Okay, so reason this guy out. 3 sig figs. Those zeros do not have a non-zero digit out in front. And then if you want, you can double check yourself. This would be 3.61 times 10 to the negative 123. So that's 3 sig figs. Okay. If it helps you to realize that we're going to be writing numbers a lot in the semester, so we keep kind of practicing this, and it does get easier as the semester unfolds. Okay, so here's some other ones to practice. These guys here are what I would call ambiguous. They are what are called trailing zeros. They don't have any decimal places involved here, correct? So if I look at 44,000, the best that's going to give me is 2 sig figs. If I look at 810, the best that is going to be is 2. And if I look at this number here, the best that's going to be is 3. So these zeros on the end with no decimal place, so non-decimal numbers, the best you're going to be able to say with them is that they're ambiguous. You have to play it conservative and just look at the non-zero digits. So this first one has 2, the second one has 2, and the last one has 3. Scientific notation is really the way to go. And I believe, let's look back, I think these were the same numbers. Oh, no, they're not. Okay. Um, Scientific notation is really the way to go because it will clarify any sort of discussions on whether the digits shown are part of the measurement or not. So if I have 4.90 times 10 to the 3 meters, because it's written in this format, remember this 0 now is going to be important because there's a number in front and a decimal point. So that's 3. 8.0 times 10 to the negative 3 would be 2. And then here, 6.0330 times 10 to the negative 5 would be all of them, 5. So any zeros in the coefficient of numbers written in scientific notation are significant. So that's why scientific notation is useful as well, because it can show us which numbers are significant figures. Okay. All right, so here's some more practice for you guys. Here's the scientific notation, 5.00 times 10 to the 2. That would have 3. 4 times 10 to the 5, that's just 1. 3.00 times 10 to the negative 1 is 3. And that's where I left off on this video lecture in class. Just one last thing. If you're looking at exact numbers, those aren't measurements. If I have 2 baseballs, it's just 2. The idea of sig figs does not apply to them. Okay. All right. And I'll end that show.